So in this video, I'd like to go over finding the arc length of a curve. So imagine the following scenario that you're basically told that you have some function, here it is, f at x, it's a function, and you'd like to know, given that you have a point x equals a and another point at x is equal to b, you'd like to find the length of this curve. So the length, what is the length? And the idea behind it, right, is basically take two adjacent points in the curve. So we can call one side as dy and the other side as dx. The length of that segment, right, of the triangle is just Pythagoras' theorem basically says ds squared is equal to dy squared plus dx squared. So we can now solve for ds. Is the square root of dy squared plus dx squared. And I'll actually do, because I know that y is equal to function of x, I'm going to try to isolate and calculate dy dx. So if I multiply by dx and times dx, I can absorb the differential dx into the square root, and you're left with dy over dx squared plus dx over dx, which is 1 dx. So we have a differential equation that says that the arc length, this little segment called ds, this segment, so we're basically looking at dx, dy, and ds. So this is a first order approximation of everything. So this is our differential equation. So I'm now going to multiply this integral, this differential, by the integral operator taken from a to b. So this is my integral operator acting on both differentials. So we can actually now, once we operate on this both sides, we see that s take at b minus s 8a is equal to x is equal to a to b ds, which is nothing more than the integral. So this is actually the length of the curve, the length between b and a. So is equal to x is equal to a to b of dy dx squared plus 1 dx. So I'll write this over here so you can actually, we'll do an example of this very quickly so I can try it out. So the length, if you want to call it s, let's make a marker. So the length, right, of this curve between b to a, or between b to a if you want to call it, is equal to the integral taken from x is equal to a to b of the square root of dy dx squared plus 1 dx. You shouldn't memorize this equation. This is an equation that you should be deriving very quickly by just using Pythagorean theorem and using first order differentials. It is, so let's now try this as an example. So let's do something like, so we're given a curve y is equal to x squared, and so here it is. I actually thought of the curve y is equal to x squared, and I'd like to find the area, the length of the curve between x is equal to 1 to maybe x is equal to 7. So the length s is just nothing more than x is equal to, from 1 to 7, of the square root of the derivative. What's the derivative of x squared? 2x, right? 2x squared plus 1 and dx. And so we'll actually solve this integral. Now the importance of solving this integral, well, it's not really that important, but this is an analytically solvable integral. but I won't spend time on this because I'm really so. As a scientist, right, you should, as a physicist, you should be able to construct differential or integral equations. The importance is that once we have a model, like some kind of a continuous model, for example, well, let's not worry about the models. You should be able to construct differential equations or integral equations very quickly. So setting up these integrals, you might not be able to solve some of these integrals, and that's fine. This one's actually solvable. It's a trigonometric substitution, but let's not bother going into it. But you shouldn't be emphasizing the integral itself. That's not important. What's important to a physicist is we construct these differential equations. We might not be able to solve them, but you should be able to construct them very quickly. Anyway, so this is for the length of a curve taken y equals x squared from x equal to 1. We can actually solve this integral, and then we'll get ourselves an analytic answer. There is an analytic answer to this.